Welcome. My name is Patrick Curran, and along with game-winning field goal kicker Greg Hancock, we make up Quantitude. We are a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In today's episode, we explore the generalized linear model as a powerful framework for building regression equations for binary and other discretely distributed dependent variables. Along the way, we also discuss stealing property, statistical conspiracy theories, mic drops, coming uncorked, getting punched by a biostatistician, big logistic, tapping out, the Oakland Raiders, being 8.5 feet tall, sheep bones, cleaning up after the party so your parents don't find out, arm strength, the regression whisperer, what we giveth we taketh away, and sultry voices. We hope you enjoy today's episode.
I don't know if you think I'm a competitive person or not, but you always have these great stories, so I would like to share a story that is just about me, okay?
I will allow it.
We were doing some landscaping in our backyard, and part of the landscaping required us to put up a fence between our yard and the neighbor's yard on the backside. We just sort of went about our business, had the property surveyed, and while the fence was being installed, the guy from the other house comes over and he stops the fence process. He is literally getting in the way of the people who are installing a fence. He brings a chair from his yard and sets it right there where they are putting up the fence. I went over to his house and knocked on the door and introduced myself, and the guy was just irate. He was in the little outdoor vestibule of his porch, pacing back and forth like a caged animal. And he is talking about how this is another example of people trying to take things away from him, and the county does it, and now we're doing it, and we must be in league with the county somehow, that there's this grand conspiracy to try to keep him from having his particular property. And I explained to him that we had an independent survey company come out, they laid down the property line, and we put up the fence inside the property line and all of that. And he said, well, how do you know that the property line is in the correct place? And I said, well, they went off the county document, so I assume that they knew how to do their job. So he stopped, looked me in the eye, and had his trump card. And he said, but you don't know about standard error of measurement. Turns out the guy's a statistician. He was worried that there could have been some great and maybe not even random deviation that was coming over to his property and encroaching on it, and then I was taking property away from him. I said, actually, I do know a little bit about standard error of measurement, so why don't you go ahead and get maybe 30 independent people to come out and do different measurements, and when you know what the standard error of measurement is and the confidence interval, then you come on back and we'll make sure. But in the meantime, we're putting up that fence. And I thought that was such a funny interaction that he thought that there was this grand conspiracy against him and statistics was going to be the key to understanding it. So I tell you that story in part because you couldn't possibly have a statistician conspiracy story. Thank you very much. Mic drop. I'm out.
Okay, that was a pen and not the microphone, and so it's not the Neil deGrasse Tyson effect that you were hoping for.
So that's right, B.O.B. The Earth isn't flat. And by the way, this is called gravity.
I love it when people play the statistics card as if that's some sure winner. They're going to bully you into some view because, obviously you don't understand. I had a funny experience once. I was working with a research group. We were around the table. It was all very good-natured. We'd been working together for years. It was pre-COVID, so I was on site at their university. They had me there as a consultant, and they had another guy who was charming and nice and funny. We had dinner the night before. We were around the table. He's presenting results on the screen. We are predicting risk factors for early onset of alcohol use. So it's a binary outcome. It is, has the child started drinking alcohol or not? So just a 0-1 outcome. And he was doing some initial models, and I started looking, and at one point something scrolled by, and I saw an R squared, an adjusted R squared. And I kind of squinted and cocked my head, and I realized he was using using a linear regression in predicting the binary outcome. Very innocently, at least I thought it was very innocently, I said, hey, I'm just curious, is this a linear OLS model? And somewhat snappishly, he said, yes, of course it is. We went on a little bit more, and I was like, okay. And I said, but it's a binary outcome. And more snappishly, he said, yes, it's a binary outcome. And then we went on a little bit more. I was like, that's not the right model for the distribution of the dependent variable. I think that it would be not inaccurate to say he proceeded to lose his And he didn't use the word conspiracy or big logistic, right? Kind of like big tobacco or whatever. He proceeded to become uncorked about how you don't have to use logistic regression, how there's no reason to do that, how we can adjust the standard errors using robust standard errors. And it really was like logistic regression was a scam.
Wow.
That had been forced upon the field, and you don't need this at all. At one point, right, you tap out. It's one of the things that we do, whether it be on the mat in a competition or when you're in an intellectual setting, is I decided to tap out.
You know I took 9 years of Krav Maga.
Carol.
You know, he's turning blue.
Our family, you gotta tap out. Tap out. Tap out.
And I said, oh, I didn't realize that. I'll have to do more reading on that. And we went on about our business. But oh my gosh, it was like a bloodbath that Big Logistic was selling the big lie that you need a nonlinear link function if you have a binary outcome.
Mostly what I heard you just do is tell me that, in fact, you do have a conspiracy theory story that involves a statistician. Damn it!
I did not realize that going into it, but yeah.
Jeez.
I think this is something fun to puzzle through because in some way it's a rather basic concept. What is the distribution of your dependent variable and how are we linking the optimal linear combination of our predictors to this response distribution that we have in our dependent variable? But in another way, this gets complicated in a hurry.
Yeah.
I think in large part it's because most of us, not all of us, but most of us are born and raised in linear modeling. We more or less have a continuous dependent variable. We more or less have parameters that enter the model linearly, and we lay down a foundation of thinking about the modeling world in per unit change over some linear relation.
Right.
When you move to a discrete outcome, and maybe just to ease things, we can focus on binary, although everything scales up in really cool ways, you all of a sudden start having things that don't behave in the way that you're used to because these beautiful, and they really are beautiful, non-linearities start to pop up, and they're hard to get your head around.
Let's just start with visualizing a very simple scatter plot. So what are some examples of X variables and binary outcomes that come up in your world?
So I could think about a continuous measure of family conflict predicting whether the child has begun using alcohol or not.
Ooh.
I could imagine high school GPA predicting whether you were admitted to a college or not. How about you?
Well, actually, you kind of hit the getting into college one. I like that a lot. Sometimes we study whether they're going to persist all the way to high school completion and what kind of predictor or predictors might we have and how early on might we have one or more predictors that can help to determine whether or not someone is likely to persist all the way to the completion of high school. There is an example that I think about, especially right now as we move into football playoffs. Do you watch the football playoffs at all? Do you care?
Back in the day I did, but I don't anymore.
Were you a Broncos guy?
Oakland Raiders.
What?
That was how I acted out. I was born and raised in Denver, and it was John Madden and the Oakland Raiders were the most hated football team in the state of Colorado, so I was an Oakland Raiders fan.
The Raiders and Broncos rivalry is as bitter today as it was in its heyday in the 70s.
I hate the Raiders.
That's my point. That's why I follow them.
All right.
So I know about football, although I don't currently follow it.
For the people who are outside the United States, when we say football, we actually mean that weird American football, not by Earth standards, real football. I think my favorite position on the whole football team is the kicker, because so many times the fate of the game comes down to the kicker. And I always thought that if I did play football, the position that I would want to play would be kicker.
Well, that's because that's the only one you and I would even remotely qualify for. We would be murdered in the first 60 seconds of a game in any position.
Wharton from his own 40. Oh, whoa! What a hit!
Other than the kicker. So yeah, run with this, Hancock.
I like this position because it's mostly a safe position, and I like that the fate of the whole game often rests on this person's shoulders.
24-yard attempt. Oh, he hits the upright! It's no good! How in the world?
And so sometimes when I think about what we're getting into, we have this binary outcome where a kicker comes up to determine the fate of the game, and the outcome is either that the ball goes through the uprights and the goal is scored, or the ball doesn't go through the uprights and goal is not scored. And thinking about the things that might actually influence that, maybe the most obvious one being how far back the kick is, right? How many yards that particular kick is. That's not exactly an academic example, but it's a fun one to think about at this time of year. So think about that as a scatter plot then. You have whatever variable you want to manipulate or observe along the x-axis. In the football example, it might be how many yards the kick is away, and then the outcome is going to be whether or not that particular kick goes through the uprights. Think about the scatter plot, though. We're so used to scatter plots looking like X and Y dots all over, maybe forming this beautiful ellipse. That ain't happening here, because your Y variable, your outcome, is either pegged at 0 or it's pegged at 1. And so there you sit with this weird scatter plot where a lot of the points are on the floor, a lot of the points are on the ceiling, and then you have to decide what is the appropriate model to try to understand that or to predict that. And this is where you ran into that tension with the econometrician.
I really struggled learning these nonlinear models because of this framework I had of linearity through all of my training. One thing that's nice to remember is take a step back to the linear model, and we have what we're used to in our scatter plot, where that XY axis within that quadrant of the plot is this beautiful scatter of individual points.
Right.
And we have a line of best fit. Even though we teach about Y sub I and Y hat sub I and epsilon sub I, what we're doing is building a model to move the expected value of that dependent variable up and down a line.
Right.
But what we want to do is to take a predictor and say, if we have a 1 unit change on our predictor X, what is the expected change of the mean of the outcome? It's a conditional mean that we're moving up and down that line. Now, as Greg just said, okay, take that beautiful shotgun scatter and you still have a nice continuous distribution of our predictor yards away, but now your outcome is either a 0 or a 1. Well, a linear model is going to try to fit a line of best fit. And if you have that XY axis and you are going to fit a line where you regress Y on X, well, it's going through that whole part of the distribution where there are no cases. It's empty. Where the guy came uncorked in this meeting was, look, we can fit a model to that, but the standard errors are going to be wrong and we need to fix those. What are the main reasons why we can't use a linear model for the binary outcome? There are a variety of them, but there are 3 big ones. One is, as you can picture a line that goes from negative infinity to positive infinity, but probability is bounded between 0 and 1, you can commonly fit a model that results in predicted values that are less than 0 and greater than 1, which are nonsensical values with respect to the distribution that we have. You should be deeply troubled by a probability of 1.1, and it's not uncommon for that to happen. Second, the residuals from that line, picture the 0s and the 1s and draw your little dashed vertical lines from each observation to the fitted line linking X to Y. They are heteroscedastic and they are non-normal.
Right.
You are violating the core assumptions of the distribution of the residuals in ordinary least squares.
Far be it from me to sympathize with an econometrician. We often have predictions on our Y that go way outside the boundaries of what's actually reasonable. So somehow we've made peace with that in some circumstances. But in this case, it's not just predicting that someone will be 8.5 feet tall. We're actually saying a probability that is outside the fundamental bounds of the definition of probability. So there's a tension between what you could do, I guess, and what you really ought to do. But you and I generally, as one of the themes of quantitude, is that as much as possible, you want the right model for the job. Pounding a line into something where you got a bunch of points up at the ceiling and a bunch of points down at the floor really isn't capturing the essence of the process that's going on here.
To be clear, I am not arguing that there are not situations in which you can fit a linear model to a binary outcome, get robust standard errors, and make an inference that is comparable to what you would get from another model that is built for that nonlinearity.
Sure.
What I am saying is, okay, we can pretend like we have a continuous dependent variable and then go in after the fact and try to fix things up, or we can select the model that is optimal for the characteristics of the data in our sample and build that in the way that is natural for that distribution. Because at the end of the day, you are not saying that a 1-unit change in family conflict is associated with a gamma unit change in the probability that you are going to use alcohol. If you fit a linear model and you get that OLS linear regression coefficient, that's across that continuum. And one of the big things is on family conflict, if you move from 1 to 2, 3 to 4, 5 to 6, 7 to 8, that a line is rise over run. We learned it all in 8th grade. Mm-hmm. The expected change in the outcome is constant over the predictor X. But picture again in your mind's eye is if we have that probability that's bounded between 0 and 1, there's actually a lower asymptote and an upper asymptote that we get this beautiful S-like curve where that's not constant change in the outcome. We have a nonlinear relation that we need to represent in our model.
There are a lot of things going on here. First of all, we don't even have probability as an outcome. We just have zeros and ones. Even though kickers either get the ball through the uprights or don't, right? The outcome is technically 0 or 1. We still think about things as being more probable or less probable on their way to a 0 or on their way to a 1. And so when you describe this beautiful S shape, you're describing that S shape to represent the way we expect predictions of probability to behave, that as X gets higher and higher, our predictions should be either peaking at 1 or at 0. In the example of a football kicker, as the yardage gets farther and farther away, we expect the probability to go to 0, that person is actually going to make the kick.
Let's start to do the math on this. This would be 76 yards. Unimaginable.
And as it gets closer and closer to, it wouldn't be 0, although you can sort of have a chip shot pretty near the goal line, we expect the probability to get closer and closer to 1. So the S shape actually captures our belief about the way predictions of probabilities ought to behave. So where we're going to go is either thinking about fitting probabilities with an S shape or taking those things and bending them to our will so we can get it back to what we're just so comfortable with, which is something that is more linear.
And to transition to that, I think it is helpful to start thinking about going to probability, then moving to odds, and then ultimately moving to what are called the log of the odds. Let's take probability.
Okay.
All right, so you're exactly right. Our dependent variable is 0 and 1, but it always, in my thinking, goes back to that conditional mean. The average of a binary variable that is coded 0 and 1 is the proportion that endorsed 1. If you have a binary variable 0 and 1 and the mean is 0.44, that literally means 44% of the individuals said 1 and the complement said 0. We can think about that as a probability. Is unconditionally, there's a probability of 0.44 that a randomly drawn individual from that sample will have endorsed 1 versus 0. All right, probability is bounded by 0 and 1. We would really like to still build a model that is linear in our predictions. We would like to have a 1-unit change in conflict is associated with some change in an outcome that's in some linear way. So we'd like to linearize the model in a way. So we can do that by moving from probability to odds. So we have to go back to the sheep bones. It always is with you with the sheep bones, right?
Scragulous.
go back to the early days, and we can define a thing called an odds. All it is a conversion of a probability. There's nothing new to it at all. If you say, we're going to assume that everything is 0, 1, where the event is 1 and the non-event is 0, and the probability of event 1 we can denote P, the odds is P divided by 1 minus P. That is the odds of the event. This comes back in the day from gamblers who wanted to say, what is the likelihood of this particular event? And if I were to place a bet of this much money, how much would I get back if the event were to occur? So horse racing, it's a 10-1 favorite, a 3-2, whatever that might be. Well, think about it. It's P over 1 minus P. Well, what if P equals 0.5? Well, 0.5 divided by 1 minus 0.5 is 1. The odds is 1. If you have a probability of 0.5, it's a 1-to-1. There's an equal probability. But now start messing around with the math, all right? And I'll have to do this in my head, so I didn't prepare these. What if the probability is 0.8?
Okay.
0.8 divided by 1 minus 0.8, 0.8 divided by 0.2 is 4-to-1.
Okay.
So the odds are that out of 5 trials, right, the 4-to-1, you add them up as 5, is if something were to happen 5 times, 4 times the event would occur and 1 time it would not. All right, so it's a 4-to-1 odds. Well, what have you done? Well, that beautiful S-shaped curve, by taking the odds, we've taken the lid off the top of that. The odds are theoretically unbounded as you move toward infinitely large. Think about going 0.8, 0.9, 0.99, 0.999. So we're halfway there. If we want to fit a linear prediction equation to our outcome, moving from probability to odds, we've taken the top off. But tell me how we take the bottom off.
Because we have a problem. We're trying to linearize this S-shaped curve, and what you did is you just sort of bent the top part up toward the sky. You helped us that way by taking the ceiling of 1 from probability, converting it to odds, but odds still can't go down below 0. So we need something that's going to take the bottom off. Odds are getting us halfway there, but the odds aren't completely in our favor.
Happy Hunger Games, and may the odds be ever in your favor.
Oh, geez, seriously? All right, so we took the top part off. Help me take the bottom part off.
There are many times where you would have said you will never have a need for this in your life, but today is that day. Taking the natural log of the odds. If we do that, we are taking the log of the odds, which is the log of P over 1 minus P. And in doing that, we now create an outcome that can go all the way from positive infinity, which it already could, down to negative infinity.
So we have linearized that relation to the outcome, which means we can still talk about beta 1 times x1 plus beta 2 times x2 in the prediction of the log of the odds. That's sometimes just called log odds, or to confuse you all further, that's the logit.
Yeah.
L-O-G-I-T. The logit is the log of the odds. Now, what's weird is this is not like a nonlinear transformation of some dependent variable, right? Is sometimes you have a skewed dependent variable and you take the natural log of y. That's a nonlinear transformation of your dependent variable. We are not doing that here. The zeros and the ones live in the wild. What we're doing is we're building this into the model where we are going to linearize the relation between our predictors and our outcomes so we can do business as usual with that linear prediction equation. But then we're going to go back after the fact and say, oh, by the way, I'd actually really be interested in getting back not only to the odds, but to the probability. And we can work our way back and forth. But you know what we need to do that? A sausage maker.
Are you bringing the sausage maker?
I can do a sausage maker. There is a remarkable approach that is called the generalized linear model. Now, for those of you like me who learned the general linear model and were told that this is the maximally general representation of our class of models, right?
damn it, we used the word general already. What are we going to do?
One would think the general linear model was maximally general, but you would be wrong. It's like all animals are created equal, but some animals are more equal than others. The general linear model is not the general expression of the model. The general linear model is a special case of the generalized linear model.
Of course it is.
We'll add this to the list of why people hate us. But what you do is you build in 3 components. And what you have is a response distribution. So you look at your dependent variable and you say, all right, what probability distribution governs this? Now, in the general linear model, that's the normal. But what the generalized linear model says is screw that. Pick anything you want from the exponential family. You have a binary. Don't rock back and forth and say it's continuous and normal. You can say, okay, it's binomial. That's just one. We have all sorts of exponential members that we can use. So part 1 is the response distribution. Part 2 is the middle part, and we're going to leave that alone, and that is the linear prediction. It's reasonable. We're not asking for too much. We're not overly greedy. We're saying, look, I would still like my usual linear model. I would like to know a 1-unit change in the predictor is associated with a beta expected change in the outcome. I would like to keep that. But you got to put the 2 together. You got to map the response distribution and the linear predictor. So the third component is called a link function. And that's the sausage maker. So if we have a binary outcome in a logistic regression, our response distribution would be the binomial and our link function would be the logit, that the conditional mean is expressed as the log of the odds. To confuse you further, sometimes people will talk about these 3 parts as the random component, the systematic component, and the link function. And I kind of like that because the random component is the response distribution. How are you introducing variability into the model? The systematic is you're trying to move up and down that conditional mean.
Right.
Can we predict the probability of a field goal kicker making a kick as a function of how far away they are from the uprights?
Statistically, the most accurate kicker in NFL history. Look at that stare. He's in disbelief.
And then the link function takes us from that beautiful S-curve, linearizes it where we fit our linear predictors, and then we can back out of it to get back to what our probability and odds are.
And all of this works together in an intuitive way. I mean, to the extent that logarithms are intuitive, what I mean by that is that we still would like to be able to think about it such that X moves 1 unit, something happens in the outcome. It's either going up or it's going down. Whether you speak logit or you speak odds or you speak probability.
And if any of you have heard the term, well, it's linear in the logits. That's what we're talking about here. We're fitting our usual linear model to the log of the odds. It is linear in the logits. But the hard thing, and this is what I really struggled with until I popped out on the other side, and now I actually really like these nonlinear models, because they talk about outcomes in a way that is so natural. Here we're talking about if a 1-unit change on family conflict, what is the difference in the odds that you will have started drinking by the time you were 12 years old? There's this incredibly natural metric to it. So what we can do is use this link function that linearizes the relation, but then the beauty is we have what's called the inverse link function. And that is you take that logit and the predicted value and you back out into the probability of the event. It's the magic of logs and exponents, because back in the day, we all learned at some point or another what the log giveth, the exponent taketh away, and we can move back and forth.
So given that we have left that safe world of linear regression, we are now in a nonlinear world that we are doing our darndest to make linear. But it means that the concept of least squares, for example, doesn't really apply, right? Because people don't have as their outcomes probabilities. Literally, they don't have probabilities. They have zeros or ones. I am very comfortable with the idea of, hey, let's bend this function and try and hit the zeros and try and hit the ones and all of that. I'm comfortable thinking about odds and probabilities. But in terms of actually estimating this thing, we're out of OLS's league completely, right?
I really like you stressing that point that individuals don't have probabilities. They have zeros and ones. And it goes back to my earlier point of we have to constantly remind ourselves we build models for conditional means. We do not build models for individual observations. Now, in least squares regression, we use that as a way to get to that conditional mean. So each person has a y. We're trying to build a model to reproduce that y that we call a y hat. The difference between y and y hat is the residual. We square them, we add them up, we select values of our parameters to minimize the sum of the squared residuals. None of that holds anymore here because we're trying to build a model for the log of the odds. Well, for the odds, we need the probability, but these probabilities don't exist at an individual level. We need a whole new ballgame.
Let's say that a kicker has a 75% chance of making a kick, and that's in general. That cuts across all conditions, every other possible variable. That's without any additional information. That means if I were going to make a prediction for this kicker at any given point in time, the probability that I would predict would just be 0.75, 0.75, 0.75, 0.75. What that would mean is that if we now had a collection of results from this kicker, every time that that kicker had a success, there was a 0.75 probability of that success. But every time the kicker had a failure, there would be a probability of 0.25 associated with a failure, right? That's unusual for this kicker who's usually successful. Now imagine that we take all of the kicks possible and we say, what is the probability of this particular collection of kicks from this kicker, assuming that all of the kicks are going to be independent and all of those good assumptions? Then we would just take the probability of each success, 0.75, 0.75, 0.75, times the probability of each failure, 0.25, 0.25, 0.25, and then in the end, we get a probability associated with that particular pattern of results. Can we do better than that? And that's what logistic regression is trying to do. Can we take information about how far away the kick is if we're doing a simple kind of logistic regression, or what the speed of the wind is, right? Either at the kicker's back or in the kicker's face, or what's the angle of the kick, right? A kick is not necessarily straight on. If we can take all of this information into account, ideally, we're going to do better than just saying 0.75, 0.75, 0.75, 0.75, right? When a kick is farther away or the wind is in the kicker's face or whatever variables we're trying to take into account, we would imagine that that probability is going to go down. And under other conditions, the probability would go up. In the end, what we're trying to do in maximum likelihood is wiggle and jiggle all of the different dials that correspond to the parameters. And the parameters are going to involve some intercept, some slope here, some slope here, some slope here, such that in the end, I will get a predicted probability for each of the particular events that I observed. And if it was successful, I would take that probability, which we hope is really a high probability. If it's unsuccessful, we hope that our prediction is a very accurate prediction of that kick being unsuccessful. And the idea then is that the probability of what was observed overall, by multiplying all of those predicted probabilities together, is going to be better than if we just said 0.75, 0.75, 0.75. That's really just a baseline. How much better can we do? And in the end, we get an overall likelihood by multiplying all of the probabilities of these cases. So in maximum likelihood, no matter what we're talking about, maximum likelihood here, maximum likelihood somewhere else, the idea is to choose a configuration of population conditions, which could mean, in this case, an intercept and slope values, for which the observed data that you have a maximum likelihood of occurring. And that's all that's happening here too. With great efficiency, we wind up getting a likelihood of our data occurring given this particular configuration of population events.
Throwing a lifeline back to least squares in our usual regression, imagine that I told you we have a sample of 100 people and the average weight is 170 pounds. And then I have you line up all the people and say, what is your best estimate of this person's weight? Mm-hmm. Well, it's 170. How about this person's weight? It's 170. Your best estimate of a dependent variable with no predictors is the mean. On average, that is going to get you closest every single time. Okay, now we're going to expand it. And when each person walks up, I'm going to tell you, well, the average is 170, but I'm going to tell you what their height is. And then the question is, can you do a better job than the mean in predicting what their weight is if I also give you their height? right? This is the cornerstone of all of regression, is does having information on the predictor variable improve your prediction of the dependent variable beyond the mean alone? And what you just described really nicely is exactly the same thing. If we just have the overall probability pooled over all their kicks, well, that's the equivalent of saying you just guess 0.75 every time. And now we're asking ourselves, well, if I tell you how far away they are, can you get a better prediction than just guessing what their career average is? And using the methods that you just described with maximum likelihood, we're able to build that into the model. The term I sometimes like, mostly because it makes people go away, you just shrug and say, well, we wrote it into the likelihood.
I like the way you contrasted it with the linear model, where you just predict it with a mean versus using something that allows X to inform it. Because in that world, we have, for example, a sum of squares associated with an outcome. You use the example of using height to predict weight. There's a certain sum of squares associated with weight, irrespective of people's height. And that is essentially how bad you're doing at prediction if you had just predicted a mean weight for everybody, right? It's a sum of squares around a prediction where everybody gets the same prediction. You're 170, you're 170, you're 170, you're 170. So that's like the worst you could possibly do. And then when you introduce the X, your sum of squares is getting smaller because you're tilting that line to be able to accommodate the people who were taller and then usually would weigh more as a result, or who were shorter and usually weighed less as a result. So in the end, you have this variability around the regression line, which is going to be smaller than the variability that you had around a mean line. So there's this inherent comparison of some baseline model that can't usually do very well at all with your new and improved linear model. And that sets us up for things like an R squared, right? Talking about what proportion of variability have we explained. That's all just right there for the grabbing in the linear model. But that gets a lot trickier when we move into the maximum likelihood world.
Me remaining the linear regression whisperer, you can have y minus y bar. That's your total variability. And then you can fit a line and you can say y hat minus y bar. And then you have y minus y hat, and you build your total sums of squares, your sums of squares due to regression, your sums of squares due to error. You get R squareds, you get F tests, you get reduction in R, you get all of those wonderful things. We can do exactly the same thing in logistic regression with the minor problem that there are no dots in that XY space.
Other than that,
Mrs. Lincoln, did you enjoy the play? So tell me, how do we use the magic of maximum likelihood to get kind of an R squared?
By kinda, you mean a fakey? Or that's what we should call it.
No, it's not fakey. We have to pretend like we're smart.
They are the fake news.
We'll call it a pseudo R squared.
Oh, I like it.
Okay, do me a favor and never talk like that again.
You don't like my sultry voice, Patrick?
Okay, dude, just pseudo R squared. Stay on task.
All right. Here's the way I think about it. If I try to draw a parallel with the linear regression model that we just talked about, there's this baseline model, which in that case predicts everybody is 170 pounds. In the kicker example, where we have a binary outcome, that's like predicting every kick is 0.75, 0.75, 0.75. So there's a baseline model that establishes essentially how much badness of fit there is in the system if you don't take any X information into account. In the maximum likelihood world, what that would be is based on what I talked about, and that is if we took all the 0.75s for the kicks that were made, all the 0.25s for the kicks that were missed, assuming that they're independent events, multiplied them together to get the overall probability. Oy, but that's a small number. I mean, that's a really small number. So what we usually do, instead of working with that as a likelihood of what we have observed overall, we'll take the logarithm of that. So anytime you take the logarithm of a product, instead, what you get is the sum of all of these logged probabilities. And that log likelihood serves as a measure of the amount of badness of fit that you have in your system by making just the same prediction for every single observation. So then the question is, if that's the total amount of badness of fit that we have without taking X into account, how can we improve upon that? when I twiddle the knobs and come up with the best possible intercept, best possible slope, and additional slopes if I have additional predictors, then I will presumably get improved probability predictions that I then fit in and get that overall likelihood, that is the joint probability of these new and improved individual kick probabilities. Take the logarithm of that, and it should be bigger in magnitude than what I had before, because I am maximizing the likelihood. And so I'm maximizing the log likelihood. So now I have a measure of badness of fit for my improved model. I have a badness of fit for a model that didn't take X information into account at all. And I can pseudo put those together in something that's a lot like an R-squared.
And then there are other approximations that have been proposed in the literature for R-squareds in nonlinear models.
There's a crap ton of them.
Yeah, and we won't go down that rabbit warren. Here, though, we can move to what I think is singularly the most confusing part of these models. We get a regression coefficient. So picture in your mind's eye, we're doing a logistic regression. You already know where I'm going with this. All right, so picture the regression coefficient. We get an intercept, we get slopes, we get standard errors, we get critical ratios, we get confidence intervals. Then I look at family conflict. It has a regression coefficient of 0.4. And I say, awesome, a 1 unit change in family conflict is associated with a 0.4 unit change in the log of the odds of the outcome. Okay. So it's linear in the logits. Now we have to remind ourselves, this is what we voluntarily chose to bring on ourselves.
That's right.
It is a linearization of a 1 unit change in X is associated with a 0.4 unit change in the logit.
Who cares if we can't interpret it, damn it?
I look at my table and there's a standard error and a critical ratio and a p-value. Everything's cool. But then there's this other column that is EXP paren B or whatever it's labeled. And that is e to the beta. Well, remember that the logs giveth and the exponent taketh away. Right, if it's linear in the logit, well, if we exponentiate that 0.4, which I see you pick up your phone right now.
What?
What is e to the 0.4?
Using my deep knowledge and ability to calculate in my head in almost Rain Man-like fashion.
82 what? Toothpicks.
It is 1.49.
Okay, which is exactly what was on your phone as you were holding it up. Okay, so help me out, Hancock. We exponentiate that to 1.49. If I want to go to a bar and get punched in the face by a biostatistician, obviously I can say, well, a 1 unit change on family conflict, you're 1.5 times more likely that you're going to onset early in alcohol use.
So if you're asking me, would I correct you right now to avoid you being punched? The answer is no.
Okay. I would expect nothing less.
Okay. After you got punched, then I might say, excuse me, I think what he meant to say is that if the exponentiated value of the slope is 1.49, that is going to be a multiplicative change in the odds. When we exponentiated it, we got rid of the log part, but we didn't get rid of the odds. So what this implies is that for a 1 unit increase in X, we would expect about a 49% increase in the odds associated with your particular outcome.
One might be tempted to call that an odds ratio. Because the odds in the numerator are at one value of family conflict. The odds in the denominator are at another value of family conflict that are differentiated by 1 unit. So the odds ratio is if you were to move 1 unit on family conflict, what is the expected change in the odds of the outcome? So all of you listening, promise us both to avoid getting punched in the face by a biostatistician that you are not 1.49 times more likely. That's not how the math works out. Your odds of the event are 49% higher. I learned that the hard way. We'll save that story for another day. But it does not mean that we have to give up our probability because, as you said, exponentiating undid the log.
Yeah.
Which left the odds. But we can undo the odds and go back to the probability. And this is something that I feel like we don't do often enough, at least in my neck of the woods. We can compute what is the probability of the event given this particular combination of our set of values in our prediction equation. Right. And this brings me to one of my favorite things, and it's the inverse link function. Our linear predictor, using the classic book and work in this area, is McCullough and Nelder out of the early 80s. And obviously hundreds of people have contributed to this. But this kind of framework was originally proposed, and even a little bit earlier by Nelder. We have this linear predictor, and we use eta, the Greek eta, to denote that. And so eta equals beta naught plus beta 1x1 plus beta 2x2, whatever model it is that we build. Eta is our linear predictor, and then we use the link function to get back and forth between that and the response distribution. There is a beautiful expression that is 1 over 1 plus e to the negative eta. You drop your eta prediction in, and you take out your calculator, and you do 1 over 1 plus e to the negative of what that value is, and that is the model implied probability of the outcome given those set of predictors.
Once you have exponentiated both sides, or as sometimes we say, taken the anti-log, then you're left with p over 1 minus p on the left side of the equation. Well, then just solve the darn thing for p, and you get that very beautiful thing that Patrick just described.
We can move seamlessly back and forth from zeros and ones to probability to odds to log odds to a linear prediction that's linear and logits that we exponentiate to go back to odds and odds ratios and work all our way back to probability. And it's all built into this entire framework. It really is elegant. We're not saying my outcome is continuous, my outcome is continuous, my outcome is continuous. We are interested in what is the probability that a 12-year-old will have started using alcohol given this information that we have about their family, and can we build a model that lives natively in those probabilities and make inferences at that same level? I think it's just beautiful.
So then I have pop quiz questions for you. Here we go. How do I determine whether or not a predictor is a statistically significant contributor to this model?
So without this turning into a grad level class, we have the regression coefficient of 0.4.
Right.
We get a standard error out of the maximum likelihood estimator. We get a critical ratio, we get a p-value, and we treat those in the same way as we would in the linear regression. However, we can exponentiate that to get the odds ratio. That is very common in what you report in a manuscript. You know what I really like is you get a confidence interval on that odds ratio. They are asymmetric.
Right.
People will often get a confidence interval on the odds ratio and then examine if that contains 1. Because remember, what is that 1 is if we're looking at a ratio of odds, what is singularly the only way we can get a value of 1 is that is if the odds in the numerator is equal to the odds in the denominator, which means that moving 1 unit on family conflict has no impact on the odds of the outcome. And so 1 is there is no effect. What we look for are confidence intervals on odds ratios that do not contain 1.
What if I'm not interested in just one predictor, but rather whether or not there's a block of predictors that are worthwhile to add? How do you handle that in this world?
Just like you do in least squares regression, except instead of f-tests and r-squared change, you have the likelihood ratio test that you so nicely described earlier. You described the likelihood ratio test of a predictor with respect to an intercept only. So could we predict probability beyond what just the overall average is? And I actually have a paper, I'll put this on the show notes. It was 100 years ago. I was at Duke. I had a wonderful graduate student at the time named Julie Kaplow. And I will put this paper up because it was her master's project. She had logistic regressions with a binary outcome, and we did block blocks of predictors. So she was interested in blocks of school level predictors, blocks of peer level predictors, and blocks of individual level predictors. And you bring those in, you do likelihood ratio tests. You say, does the block of peer predictors uniquely contribute to the model above and beyond the demographics that were already entered? And then within that block, you get the unique prediction of each predictor above and beyond all other predictors in the usual way.
So you and I have been very specific in focusing on binary outcome and a certain class of models right now within the Logit family. How do we stick a shoehorn in this and make it bigger? Because this has to be part of a much, much bigger neighborhood.
Maybe this one is I can do like top 10 greatest hits.
Hello again, everybody. Welcome to America's Top 10.
Before we exit the logistic regression, pretty much on the X side of your model, anything you're used to in linear regression, we can do in the logistic. We can have main effects. We can have interactions. We can have quadratic effects. We do not make distributional assumptions on the predictors. You can have counts. We can have dummy codes or effect codes to capture nominal grouping variables. So rent a van, go to Orlando, X side is go nuts. But now, very briefly, maybe I will inhale and try to say it just in whatever one breath is so that we don't add another 45 minutes. Everything we've talked about has been the binary outcome. But the beauty is, if we take the McCullough and Nelder kind of approach of having a random component, a systematic component, and a link function, dude, we're off to the races. We can say, okay, you start to see that the general linear model is one member of that generalized. And we haven't articulated this, but the general linear model is a generalized linear model with a normal response distribution and what's called an identity link function. That is, there's just a one-to-one correspondence. We don't need a sausage maker. Well, what if we have an ordinal variable? So let's say instead of binary, 0, 1, we have 0, 1, or 2. And here order matters. You have a parent reporting on a child's symptom and they say there's no evidence of this at all. There is some evidence or there's clear evidence, 0, 1, or 2. We just scale up the logistic into what's sometimes called a proportional odds model. So we build a model where we map family conflict onto not just moving from 0 to 1, but from 1 to 2. One that's really cool in my neck of the woods with substance use research is, what if you have a count? All right. So I'm studying substance use and I say, in the last 7 days, how many alcoholic drinks have you consumed? 0, 1, 2, 3, 4, 5. The response distribution for that would not be binomial because those are not independent binary events. We might pick one that's called a Poisson distribution. Another one that I like is a negative binomial distribution. These are members of the exponential family. McCullough and Nelder say, dude, go nuts. Well, also in my neck of the woods, we have things that are called zero inflated models. So I'm looking at drug use in adolescence. Thank goodness most kids don't use, but what you get is a piling up at zero, a zero inflation. Well, you get to this condition that's called overdispersion. And this is a whole nother episode, but the Poisson, the mean, and the variance are equal. And in an over-dispersed model is that the variance is greater than the mean. Well, we can build zero-inflated versions of this. Sometimes you hear about zip modeling. It's a zero-inflated Poisson. But what's so cool about this is we can move into what are called two-part models. We can simultaneously build a model for are you zero or not zero, while building a model for if you're not zero, then modeling how many are you.
Yeah.
I think it's really exciting to think about the ways that we can do this, not rocking back and forth and saying, it's linear, but I'm fixing the standard error. It's like, dude, take a deep breath, lean back in your chair, tell me what the response distribution is, what your linear predictor is, and how you're going to link them together, and we can do anything we want. I don't want to be punched in the face in my driveway by an econometrician. I understand There are situations when you can fit a linear model to a binary outcome and correct the standard errors. My view is simply, why go in and clean up after the party so your parents don't know when we could build a model from the ground up that represents the data as we believe it exists?
I will tell you, I tried to run a multinomial model one time, but no matter what I did, it didn't converge. But you know what I think the problem was? It was too legit to quit.
Did you learn nothing from the Haywood episode? Did you learn nothing at all?
Maybe I should have hit it with a bigger MC Hammer.
You can't touch this.
Nothing?
Nothing.
Thanks, everybody, for letting us describe a little bit about how logistic regression works. We hope it was useful to those of you who aren't so familiar with it, and maybe to help you see what some opportunities might be for you so that you can help choose the models that are best suited to your data.
And there's some really nice tutorial-like pedagogical treatments out there, and we will post some of these on the show notes. I think that it's one of those things, like when you start jogging and it just sucks, but just know on the other side of it, it's good.
And don't get punched by a biostatistician.
Yeah, econometricians are okay because they're pretty slow and don't hit that hard.
No arm strength whatsoever.
No arm strength at all. Biostatistician, you're going to get your ass handed to you. Take care, everybody.
Thanks so much for joining us. Don't forget to tell your friends to subscribe to us on Apple Podcasts, Spotify, or wherever they go for dated movie and music references and mediocre dad jokes. You can also follow us on Twitter, where we are at QuantitudePod, and visit our website, quantitudepod.org, where you can leave us a message, find organized playlists and show notes, listen to past episodes, and other fun stuff. And finally, you can get cool Quantitude merch, like shirts, mugs, and notepads, from redbubble.com, where all proceeds go to donorschoose.org to help support low-income schools. You've been listening to Quantitude. We put the odd in log odds. Today's episode has been sponsored by hypergeometric distributions, way more excitable than regular geometric distributions, and by polychoric correlations, the coolest correlation coefficients there are, uncategorically. And finally, by censored data, because and the but only because this is most definitely not NPR.